Relative Velocity 2014, question 2, part A. So 3 ships, X, Y, and Z, are observed from a Coast Guard station at half-hour intervals. That could be important. With distances measured in kilometers and speeds in kilometers per hour. And they have the following displacement and uniform velocity vectors. So we have a lighthouse or a Coast Guard station at 2 o'clock. 2 o'clock observes X to have a position relative to, I'll just move this up a tiny bit. So if we imagine the Coast Guard is the origin, at 2 o'clock X is approximately here. Let's say X is here, and this is the Coast Guard, and that's 2i plus 7j. So in an hour's time, his velocity is 4i plus 5j. In 1 hour's time, he's going to go out 4 and up 5, and he's going to continue with this slope in a continuous motion in this direction until he runs out of fuel. Now, what else is happening? We have proved, part 1 is X and Z together, so let's look at the two of them together. Prove that if X and Z continue with their uniform velocities, they will collide, and find the time of the collision. Okay, well, this was X at 3 o'clock, X at 2 o'clock, and we have Z at 3 o'clock is in a position of 12i plus 9j. So if we imagine that this is 2 o'clock after 1 hour, this is 3 o'clock, and Z is in a position 12 plus 9, so he's out further. That would be 6 plus 12, so that's out 6 at that point. So we want to go out 12 and up 9. So we somewhere like this, let's just say here. And he's going 2 plus 6, so out 2 and up 6. Out 2 and up 6. But we better make it a bit steeper, they look like they're parallel. Out 2 and up 6, out 2 and up 6. So he's along this trajectory. And you can see they are going to collide at some point. So, prove if they continue with their uniform velocities, they will collide, and find the time of the collision. So let's see where X is after an hour. So X starts at 2i plus 7j. In 1 hour, we add 4i plus 5j. In 2 hours, we add 4i, thinking T, in 2 hours we add 4i plus 5j times 2, and in 3 hours 4i plus 5j times 3. So we can call at any time the relative position of X, we can call it R of X. The relative position of X is going to be 2i, and we keep the i's together, plus 4it. I'll put the t in front now, and then we have plus 7j plus 5j t. So that's 2 plus 4t times I. And we have plus 7 plus 5t times j. So that's the relative position of X. Let's look at the relative position of Z up here. See, can we get them to match? Or how can we show that they're going to match? So the relative position of Z at any point is going to be 12i plus 9j. And the key to this one is that you're going to be adding 2i plus 6j. Now it's not times t, it's times t minus 1. So when t is equal to 1, this is 0. So the relative position of Z is where it is observed after 1 hour, and the relative position of X is if t was equal to 1. So that's why we have to have a t minus 1 here. So this, the relative position of Z, is going to be 12i plus 2i t plus 9j plus 6 tj or jt, and then we have the minus 2i and the minus 6j. So we're going to have 10i And then, so if we take out the t, we're going to have, or sorry, if I take out the I, we're going to have 10 plus 2t. So that's 12 minus 2, 10i, and then the 2t times I. That's just not a very clear t, 2t times I. And then j, we're going to have 9j minus 6j, so we're going to have 3j. So plus 3 for the 3j, and we have plus 6t. So we just need to equate one of them. Are they the same? If we equate I to be the same and our value for t allows j to be the same, then we can say that they're at the same place at the same time. So 2 plus 4t is equal to 10 plus 2t. So 2t is equal to 8. So t is equal to 4. So that would make this 3 plus 12. Sorry, 3 plus 6 fourths, 3 plus 24, which is 27j. And this one down here is 7 plus 20, which is 27j. So after 4 hours, when t is equal to 4, they will collide. And we start at 2 p.m. So 6 p.m. here is the time of the collision. And then at the instant of the collision, ship Y changes course and then proceeds directly to the scene of the collision at its original speed. So let's just take any position for Y. Let's take this position over here at Y. So they collide and Y changes position and immediately goes to here. So Y was here and it's going over to this position here. We'll call, there's no B in the question, we'll call it B. So we're asked to find the time to the nearest minute at which Y will arrive at the scene. So we have a distance. So we're looking at distance, speed, and time. All we have to do is decide which ones we have. We're looking for time. They've asked for the time. So we distance and speed is what we're looking at here. And they tell us it's the original speed. So we know all we're looking for here. We need to find the distance that Y is away from the collision. So at 6 p.m, where is Y? Started off at 6i plus 9j. And then it's going to be 2:30 till 6 o'clock is 3.5 hours. So 3.5 is t and the velocity is 3i plus 4j. So this is the relative position of Y. What's that equal to? 6i plus 10.5 plus 9j plus 4 3.5 or 14. So you have 6 plus 10.5 is 16.5i plus 23j. So this is the relative position of Y in relation to this crash, or in relation to the Coast Guard. So where did the crash occur? What was this position? We have two positions now. We can find the distance between them. It was 27 in the J. Did we actually even work out the I? We didn't work out the I. 2 plus 4t. T was equal to 4. So that's 18i here. So 18i plus 27j. So the crash is at 18i plus 27j. So one vector is here and one vector is here. How far apart are they? Well, what's the difference in the I direction? It's 1.5 we can see here. And the change in the J direction is 4. So we're looking for the square root. This will give us the distance between them. The square root of 1.5 squared plus 4 squared is equal to, give me 4.272, which will be kilometers. So that's the distance away. And the speed that Y is going at is down here. It's the velocity. So the magnitude of the velocity of Y, well, we can see here it actually works out evenly. The square root of 3 squared plus 4 squared, which is 5. So we're looking for time, distance, speed, and time. Time is equal to distance over speed, 4.272 divided by 5, which is equal to 0.8544. That's 0.8544 of an hour, and we're asked to the nearest minute down here, so I'm going to multiply this by 60 to get 51.264 minutes. So to the nearest minute, 51 minutes before y gets there.